Okay, 2017 Leaving Cert short questions, section A. Let's give this a quick look. Now I'm going to try and zoom in there a little bit more. So A1, we've got a Bluetooth mini speaker that's in the shape of a cube with the faces with notches cut out of them or grooves. Drawing on the right shows the axonometric. Complete the axonometric projection of the cube and the given lines. So there's basically a very good 3D of it there, showing that there's 3 lines on the top surface and 2 on these surfaces. So in the top view there's 3 lines across the top surface. So the first thing I might do there is complete the cube maybe. So I might just color in some corners there in a second, but I'm going to complete the cube here first. So I'm going to bring up this corner and project down. I'm going to label this as well, so that's corner C and corner D. So I'm going to decide that this is A and B. So that's up here corner A, and back there is corner B. And when I complete the cube, there is our completed cube. Now the lines on the top surface, again there, just to help people understand this, I'm going to put some color on the top. Again, I've said this here now, I'm going through these questions more as a way of teaching the stuff rather than in the exam situation. You're going to be answering these as quickly as you possibly can and just moving on. But I'm going to just try and teach the stuff as well. So I'm going to colour in that top surface there in yellow, because as I've said previously, I think using a few colours helps greatly people to visualise and understand these things. So there's our top surface there now in yellow. So the lines on the top surface, I could bring them down from the elevation or up from the plan, but I'm going to bring them up from the plan. So that's on the top surface here, going to this point. So I'm going to draw this line in here now. I'm going to draw these in as I go. It's the safest thing to do. So I was saying there's 3 lines on the top surface, and that's one done. The second one is crisscrossing here. That is 2 of them done. And finally, that point there, point here. Okay, so that is the 3 lines on the top surface done. Now the CD line, again, I am going to go to the bother of putting some colour on this. So I'm going to just highlight that face there in blue or cyan. So that is the CD surface, which is up here. Just so we can see where some of these lines are coming from. So they've already done the CD line. So the CD line is done. So it's the AB line that I want here. So I'll just line that up again. So B is on the ground. which is there. A is at the top. Okay. So I'm just going to index this as well now. So that's line B there. And that's A. So finally now on the front surface here, I'll just give this a light color as well. So that is red. I'll just color this in red as well. Okay, so the bottom of that line on the ground is here. There on the top. And then crisscrossing the other way, I have that second groove on the edge, and that is going to D. Okay, so that now 2 lines here, 2 lines there, and 3 on top. So that's all of that done. Now the second part of this there then was determine the true angle between the lines AB and CD. Now the true angle between AB and CD is on the 3D pictorial over here. You can see what you need is a true orthographic view of this. So here's our person looking in there, left foot and right foot, and they're looking in here. So if I was looking in straight at that angle, I would see it. So I think this is possibly the most straightforward way of doing it. So I'm just going to project that up there. It's like taking an auxiliary, set up an XY line. Okay, since this is a cube, well, I could take my height from here or from here, seeing as it is a cube. So I'm getting there to that's 31. And what we need to find now is AB and CD on this. Now, one way of doing it is I could project point A down. Well, we know A, and we know now if I bring B down to the plan, that's the location of B. So I'm going to do this one first. So when I project that up here, point A, I label it here as well. So A is on top, B is on the ground. So that now is the true shape of that surface and the true length of AB. And then I need to bring C and D. Now, because these are true heights here, I can bring the heights of C and D. Now it's important to understand that that axonometric is not a true shape of the surface, but because or that side view there is not a true shape, but they are the correct heights, they're the real heights. So that is C and D. That's C, that's D. And the question said the true angle between AB and CD. So I'm going to just indicate that on one of these here, just to indicate that you answer the question. And that is the first one done. Now the second question here. The drawing on the right shows the axis AA1 and the directrix and the focus F of a parabola. Now the second you say, so the main curve is a parabola and the club shaft is a normal to the parabola. So the second you see parabola, you should be thinking 45 degrees for the line of eccentricity. If you have covered your conics, which I will do again on a separate video, so the line of eccentricity is 45 degrees always. Eccentricity, which is the distance from the point focus to the point to the directrix, is 45 degrees. Is an equal distance. Okay, so however far any point is on the curve from the focus, it is the same distance from the directrix. Now, some other important stuff that you should know. Again, this is not looking at teaching this from scratch. This is basically aimed at people that have covered some conics in class and that know some of this stuff. Is that the line that goes through the focus here is called the latus rectum, and where that intersects the line of eccentricity, that is a point on the curve. And because the parabola is symmetrical, I can take this distance, step it down, and that's 2 points in the curve. And the other thing, a property that is common to all the three conics that come up like this, ellipse, hyperbola and parabola, is 45 degree angle up to the line of eccentricity and back down again. I'll stick an arrow on these as well. Gives us the vertex. Okay, so we now have 3 points on our curve. I'm going to take a couple of more, so just a random ordinates. This many will do me. Some random ordinates. And I will just take there. This is the distance PF. So the distance from the point on that ordinate to the focus is there and here. And take 2 more points. So that the distance from the focus there. So I might put this in red just to help it stand out. So our elliptical or our parabolic curve is there. So we've located the vertex, drawn a portion of the parabola. So the next thing I want to do is locate a point P on the curve that is 30 from the directrix. Okay, so 30 from the directrix would be over here. And I could do this above or below. I'm gonna go for the option below. Okay, so locate point 30 from the directrix and construct a normal to the curve at point P. So that's my point P there. Now again, I touched on this before, and I'll just sketch it here. If it was an ellipse and we had 2 focal points, and if you were looking for a tangent or a normal, you would be joining to the focal points and bisecting the angle. So that would be the normal and perpendicular would be the tangent. So that's if it was an ellipse. Now because it's a parabola, the thinking is that the second focal point is at infinity, which is a horizontal line. So that is going to infinity for the second focal, and my first focal point is here. Okay, so I'm going to bisect that angle. So here is the normal. Now if I wanted to draw a tangent, which I wasn't asked, but if I wanted to draw a tangent, then it would be 90-degree angle perpendicular, so that would be the angle for tangent, but they specifically said the normal. So that's A2 answered. Now A3, using so there's a fireplace there based on a regular solid, and all the faces are regular pentagons. So it says, using the given xy, draw the true length of the line of intersection between A and B. So the line of intersection between A and B, I'm going to call that 1 and 2. That 1, 2 line there is the line of intersection, and down here in plan, that's 1 and that's 2 there. And I'm going to need 2 other points, so I'm going to pick, well, I could pick a point 3 and a point 4 up there, or I could take them on the ground here. I think I'll choose to take 3 here and 4 here. So I have the line of intersection, this being the key line here. Just not sure how well that color comes out there now, but I'll just try and put some color on that we might see. So 1, 2 being the key line here, the line of intersection, and I'm going to just project down so that I don't make any mistakes finding these in plane. So that's my point 3 there, and over here on the ground is my point 4. So that had been started off for us. So we need to get the true length of the line of intersection. So 2 is here on the ground. I'm also going to bring 3 and 4, which are on the ground. I'm going to mark them. So that's 3 and 4 there on the ground, and 2 is here on the ground. Finally 1. So I'm projecting from the plane, so the last XY line back. So here is my height for 1. So that is the true length of 1, 2. I'm going to stick with my coloring system now. So the true length of 1, 2 is there. 1 and 2, and 3 and 4 here. Now finally I need to look along. I'll just index that TL for a true length. So we want to look along TL and get a point view of it. So just project out there, put an XY line anywhere. I'm going to bring 3 and 4 as well. So I'm projecting from this view, so it's from the last XY line back. So my distances are going to be, I will just get the point view first of all of 1, 2, and again why it gives us a point view, because when you're looking along 1, 2, the distance back to 2 and the distance back to 1 are the same distance. So when I look along here, that is going to give me a point view of 1, 2. And then I also need to get distances now for 3. And 4. There's 3, there's 4. So my dihedral angle is there. Be sure to indicate it in theta degrees. There's our dihedral angle. Now, the second one there then says determine the center point of face B in plane and draw the projections of a sphere which rests on the horizontal plane and is also in tangential contact with their center point of face B. Okay, so basically we're looking to put a sphere on the ground up here. Just sketching a quick sphere here. We want to put a sphere on the ground up here that's sitting on the ground, and it's in contact with the center of that face B. Okay, so step 1 anyway would be to find the center point of that face. Now, an easy enough way to do that would be if I just join cross corners here, or from any corner to the center of the edge opposite is going to be going through the center. So once I bisect any of these lines here, now that works out as 16, which would mean that the center of that is there. So that would be the center of that line there. So that line joined down to 2. So that there is the center point of that surface, because the line going from this top corner here, if I bisected the middle of the side opposite, that is going towards it there. So that's the center of the face. Now the next thing I need to do now is I need to get an edge view of that. So if I take an auxiliary along there, put an XY line up here, so there's the ground. This is going to give me an edge view of that surface B. So I'm going to need some heights here now from the elevation. Okay, so that's the height of the first 2 points. Because this is an edge view, there's an edge view of surface B. So the next move after that there then is, and I need to bisect the angle between that and the ground. So again, when it comes to bisecting, bigger is better. So I'll just mark a distance out there. Just take 2 more arcs. So that bisects the angle. I'll just put that in a color to help maybe people see it. So that's the bisect. Okay, so that bisects the angle there. I'll just heavy that in a little bit. And now the point of contact had to be touching at C, the center of the face. So I've got to bring that center up to here. There is the center of the face, this point here. And if that's the point of contact, that is the point of contact, the center has to be 90 degrees to that. So this must be the center and the radius. So I will just draw that sphere in there as well and set my radius. And then when we project that down, so coincidentally it's pretty much in line with the corner there. So there's the center. There's the center for the sphere, and when I project that back up then, so I've got 2 points marked center here because I've got the center of the sphere and I've got the center of the face. So the center of the sphere is here. And then that is sitting on the ground. And finally there, I'm going to mark as well the point of contact up here. So the center point of the face is the point of contact, which is up here. So I'm going to just project that up there, and I'm going to take the height of that point as well. And just step it up there. And that's the point of contact there. Okay, so the center point of face B, draw the projections of the sphere sitting on the ground, touching there in the center of the face. So that's A3 sorted. Now this one there, so plan elevation in view of an archery target. PA represents the plan of the arrow just before it hits the target. And the arrow is traveling horizontally in a straight flight path. Now I'm going to just highlight there, a key word here is that the arrow is traveling horizontally from P, which means that if the arrow is traveling horizontally from P, it is going to hit here. And I'm going to just bring the height of that across, and since the arrow is flying in a straight line, it's going to be coming in here. Now what I need to do there then is I could bring this point and that point down, or one of them would even do there on the edge of the ellipse. So it must hit the target on that line. I might heavy these lines in so that, because I'm not sure how good they're coming out on the video. So the arrow has to hit on this line, And since the arrow flies in a straight line, that is where it hits. And when I bring that point up to elevation, so that there is basically the arrow flight in elevation, because P is here in the center, and I'll just call that X, where the arrow actually lands. So draw the elevation, draw the arrow of PA in view and in the elevation. Okay, so determine the projections of the arrow when it hits the target. Okay, so I think we have all that covered and sorted. Like another way I could have done this is I could have brought down and rotated that around to get that line and brought it across, and that would have given me point X as well. That would have been an alternative way of doing it. So a second arrow traveling in a straight line also passes through point P and hits the target at the bullseye. Now I'm going to change colors for this. Okay, so the bullseye being here is there. So this arrow, I'm going to draw it in here in color. So you'll notice there that this arrow is going downwards. Okay, so that may change things a bit. We need to think about this. So a second arrow traveling in a straight line also goes through point P and hits the target at the bullseye. Determine the true angle between the two flight paths. Okay, so the second arrow in plan is going to here. Maybe I should just put that in black. It might be easier to see it. So I'm going to call that, where that point hits, I'm going to call that point Y. And in elevation, seeing as here's the bullseye, just draw that in there. That's my point Y at the bullseye. So it says determine the true angle between the two flight paths. Now, I think the easiest way to finish this question off would be if I was to make a triangle out of this. So I've got a triangle PXY, PXY. And again, that's a triangle. I'll just put a little bit of color on it here just so you can see what I'm talking about. So that is a triangle there now. And we want the true angle between the two flight paths. So basically we are looking for the true shape of that triangle. So P to Y, P to X. We are looking for the angle at P, the true angle that is there at P. So options are, because PX is horizontal line, if I look along PX here in plan, I would get a point view of that and an edge view of the plane, and I could then take an auxiliary off it. That would be one option. But I would be always looking out for a quick way to do these questions if you could. Now P to X here is horizontal, and there's P to Y down here. But since PX is horizontal here, that is a PX is a true length here. Just mark that and their true length. Px is a true length here in plan, and if we had the true length of Py, okay, which we do have over here, that is a true length, and the in view, should I say, is a true length. So what I could do there is I could take the true length of Py, and if I swung that true length of Py here, and you need to, I guess, understand your revolving a shape along a line. But if I revolved this triangle along the horizontal px or px line there, it would mean that y would move out 90 degrees to that axis of revolution. Now I know this is only going to be moving a couple of mil down here, but it's an important couple of mil. So I'll just put an arrow there, so this here would be my true shape. And I'm going to put this in red. Okay, so the true shape. Okay, and that's a really quick way of doing it. So Px was a true length, Py was a true length here, and when I swung that arc, if I was spinning that triangle around, I guess it would be like spinning a set square around, the corner moves 90 degrees to the axis of revolution. That is the quickest way of doing it, but I will look, because as I said, I'm not looking to do these as fast as possible on the video. So let's say I took a xp is horizontal, so xp is a true length and plan. If I looked along that, set up an xy line down here, and what I could do then is I'm projecting from plan, so I'm going to be taking my distances here. So x is going to be up there, and p, and y is this height. Just need to project y. So that there is an edge view of that triangle. That's y, that's px. And if I took one more view now, which would be 90 degrees, so that there is the edge view of the plane. So if I took one more auxiliary down here at 90 degrees, project, oops, put an xy line here. So I'm projecting from here, so it would be from the last xy line back. So here's my distance from y. There's y. Here is x. T is that far down there, just have to extend this down. Just double checking my Y there again to make certain I marked that one right. Did. So there. So again, seeing as I used orange over there, red, I'll just color that in there again. I'm going to stick a TS for true shape on it. Probably more ways that you could do that. I mean, you can always do it by getting 3 true lengths and swinging arcs, transfer of distances, I think I would call it. But yeah, there's always 3 or 4 different ways of doing those true shapes. So there is a 4 finished.